Let's move on to section 2.2, the standard enthalpy change of neutralization. It has a symbol of delta Hn, N stands for neutralization. It is defined as the heat evolved when 1 mole water is formed from the reactions of an acid and an alkaline under standard conditions of 298 Kelvin and 1 bar. The enthalpy change of neutralization is always negative. It is an exothermic process because to form 1 mole water from an acid and alkaline, it would involve H plus from the acid, OH minus from the alkaline to form a bond between them in order to form water. So this is a bond formation process, and therefore the reaction is exothermic. And if the reaction involves a strong acid and strong base, the enthalpy change of neutralization will be equal to minus 57.3 kilojoules per mole. Enthalpy change of neutralizations can be determined experimentally and is given by this equation. Delta Hn is equal to minus Q over N. N is the amount of water formed based on definition. So the per mole in the units refer to per mole of water formed. So in the thermochemical equation, to represent enthalpy change of neutralization, it will involve aqueous acid and aqueous alkaline to form salt and water. And equation, the amount of water must be 1 mole. If the equation shows 2 moles of water, for example, 2 moles of sodium hydroxide reacting with 1 mole of sulfuric acid to give salt and 2 moles of water, then this equation will represent 2 times the enthalpy change of neutralization. It is not enthalpy change of neutralization. Let's look at table 2 closely. These are the strong acids. These are the strong bases. If the neutralization involves a strong acid and strong base, then the enthalpy change of neutralization is always equal to minus 57.3. It will give a constant value. Let's look at this table. These are weak acid. This is ethanoic acid. It's an organic acid. Organic acids are weak. Ammonia is a weak base. Organic bases are also weak. If the neutralization involves weak acid or weak base, or both weak acid and weak base, then the enthalpy change of neutralization will be less exothermic than minus 57.3, which means less heat is released for per mole of water formed. So let's look at the reason why. Strong acids and strong bases ionize completely in water prior to neutralization. If you have a beaker containing HA aqueous solution, which is a strong acid, then you would not be able to find any HA molecule in the solution, as all the HA molecule would have fully dissociated to form its aqueous ions. Just like hydrochloric acid and sodium hydroxide, they would have completely dissociated to form its aqueous ion in solution before neutralization. And to represent full dissociation, we use full arrow in the equation. So when the strong acid and strong base are mixed, it's like mixing H plus and OH minus directly to give water. So we can represent enthalpy change of neutralization for any strong acid and any strong base using this equation. And therefore, the enthalpy change of neutralization involved a strong acid and strong base is the same as equal to minus 57.3. It's a constant value. For reaction involve a weak acid or a weak base, note that weak acids and weak base only ionize partially in water prior to neutralization. In a beaker containing aqueous HA solution, which is a weak acid, example ethanoic acid, you will find many unionized HA molecules still remains in the solution. Only partial of them have dissociated to form its aqueous ions. Same idea applies to a beaker of aqueous weak base solution. There will be many unionized weak base molecules in the solution, and only partial of them have dissociated into its aqueous ion. For partial dissociation, we use reversible arrow in the equation. So for reaction involve a weak acid and a strong base, or a strong acid and a weak base, or a weak acid and a weak base, to form 1 mole of water from 1 mole of H plus and 1 mole of OH minus. Some heat has to absorb to fully dissociate the unionized weak acid or weak base molecule. So overall, instead of 57.3 kilojoules of heat is released when 1 mole of water is formed, because some heat has been absorbed from neutralization to fully ionize the remaining unionized weak acid or weak base molecule, less heat is released. So the enthalpy of neutralization will be less exothermic. Let's complete exercise 5 together to see how the enthalpy change of neutralization can be determined experimentally. In this experiment, you are mixing 250 cm³ of aqueous sodium hydroxide with 250 cm³ of aqueous sulfuric acid in a styrofoam cup, in a polystyrene cup. Before mixing, you will measure the initial temperature of each solution, then obtain an average initial temperature of the solution, which is given to be 26.0 degrees Celsius. I will draw a setup for the experiment to remind myself total volume of the solution added to the cup. After mixing, the temperature of the final solution is measured and the maximum temperature reached is found to be 28.4 degrees Celsius. You are given 4.3 joules of heat is required to raise the temperature of 1 cm³ of solution by 1 degree Celsius. So to calculate Q, which has a unit of joules, you need to take 4.3 times V times delta T, where V is the total volume of the solution in the cup, because the temperature change is the temperature of solution in the cup. Since there's no other information given in the question, we assume that the heat transfer is 100% efficient and the heat capacity of the calorimeter is 0, which means the plastic cup does not absorb heat from the reaction. So all the heat released from the neutralization is absorbed by the solution in the cup. So the heat change Q of the reaction is the heat change of solution in the cup, which is equal to Vc delta T, where V is the total volume of solution in the cup, which is 250 plus 250, times C, which is given to be 4.3, and delta T in degrees Celsius. And the answer for Q will be in joules, convert to kilojoules, 5.16 kilojoules. Then you will proceed to calculate the amount of sodium hydroxide used in the reaction and amount of sulfuric acid used in the reaction. From the mole ratio of 1:2, you will determine who is the limiting reagent. So from here, clearly sodium hydroxide is the limiting reagent. To calculate enthalpy change of neutralization, which is equal to minus Q over amount of water produced, I will need to know amount of water formed. So from the limiting reagent, which is sodium hydroxide, the mole ratio of sodium hydroxide to water is 1:1. So the amount of water produced is the same as amount of sodium hydroxide. And since temperature rises, the enthalpy of reaction is negative. It is exothermic. So the enthalpy of neutralization is given to be minus Q, which is 5.16 kilojoules, divided by amount of water formed, that is 0.1. It turned out to be minus 51.6 kilojoules per mole. Do notice that this is a reaction between a strong base and a strong acid. And why is it that the enthalpy of neutralization calculated is less exothermic than minus 57.3? The only reason you can think of is the assumption is not valid. The heat transfer is not 100% efficient. Some heat is lost to the polystyrene cup, which means some heat is absorbed by the cup. The heat capacity of the cup is not 0. And some heat may be lost to the surrounding air, which means the system is not perfectly insulated from the surrounding air. In exercise 6, you are given the standard enthalpy change of neutralizations of hydrochloric acid and sodium hydroxide to be minus 57.3 and that of sodium hydroxide and ethanoic acid to be minus 55.2. Do note that sodium hydroxide is a strong base. Hydrochloric acid is a strong acid, but ethanoic acid is a weak acid. You are to account for the difference in the enthalpy change value. We have noted that sodium hydroxide is a strong base. HCl is a strong acid. Both ionize completely in water. So hence when mixed, it is equivalent to mixing H plus and OH minus directly from the strong acid and the strong base to form water. And therefore the enthalpy change of neutralization is minus 57.3 kilojoules per mole. Ethanoic acid is a weak acid that ionizes only partially in water. So in a beaker of aqueous solution containing ethanoic acid, you will have many unionized weak acid molecules in the solution. Only partial of them have dissociated to form its aqueous ions. So during neutralization, some heat from the neutralization is absorbed to fully ionize the remaining unionized weak acid molecule. So overall, less heat is released and the enthalpy change of neutralization is less exothermic. For part B, you have to calculate the enthalpy change for the full ionizations of the ethanoic acid to form its aqueous ions. So this is the equation that you want to find. And the given enthalpy symbol is delta H. So when the weak acid is mixed with sodium hydroxide can be represented by OH minus because it's a strong base. The given enthalpy value is minus 55.2. It will form water and give CH3COO minus after the reaction. When the weak acid is completely ionized, when OH minus is added in, it's like mixing H plus and OH minus to form water. And this given enthalpy value is minus 57.3. So to calculate delta H, you find that from the given diagram, delta H plus minus 57.3 is equal to minus 55.2. So the delta H, which is the enthalpy change of reaction for full ionizations of ethanoic acid, will be equal to plus 2.10 kilojoules per mole. Or you can simply solve by understanding that for complete neutralization to form 1 mole of water from 1 mole of H plus and 1 mole of OH minus, the heat evolved is 57.3 kilojoules. Since only 55.2 kilojoules of heat is released when mixing sodium hydroxide and ethanoic acid, then 2.1 kilojoules of heat from neutralization must have absorbed to fully ionize the remaining weak acid molecule. So heat is absorbed for ionization, the enthalpy change is positive, and therefore enthalpy change of reaction delta H for full ionizations of acid is plus 2.10 kilojoules per mole. Next, please do self-assessment 1 as homework. Your teachers will check your answer.